Hello, welcome to video 3 out of Unit 3, which will look at potential energy and the conservation of energy. Conservation of energy is going to be an important problem-solving method that we'll use in this class, being that it allows us to skip a lot of middle steps. A lot of intermediary steps are taken out of the way as long as we understand how energy is conserved or is lost in some cases due to friction. One way or another, using the ideas of work and energy, we can solve a lot of fairly complicated problems in an easier way. So, there is some information on the board before you. Please record that. Pause the video now so you can take a little time to write this down in your notes. I'll be talking too fast for you to write it down when I go. So, the work done by a conservative force on a particle is independent of the path which it takes when it moves from one point to another. So, let's consider, and back again, obviously. If we consider a ball, if I was to simply drop the ball, the work done by gravity doesn't really change if I was to drop the ball, going from here to here, or if I was to toss it to the side, allowing it to fly in an arc. It would still have the work done by gravity from here to here. And if I was to bring the ball back up to that same height, no matter which path I took to get to that exact same starting point, I would still be working against gravity, the same displacement against the same force, which means if I was to add my work done by gravity, force of gravity times displacement, mg times delta y, and then add to negative mgy, because now I am storing energy in the potential, or storing energy for gravity to use, I would get an answer of 0. You add those two together, you get 0. It wouldn't matter which way I took to get there. No matter what, I would still be using the same displacement. The work done by gravity still works within that same displacement delta y. It doesn't matter where I go horizontally or in or out for z. A good example of conservative forces, obviously, we've already said, gravity. Turns out the force of a spring is also quite conservative. It does the same amount of work compressing as it does stretching. So if we add the sum of those together, the positive work going in is the same as the negative work heading out. Therefore, it equals 0. So forces of a spring are also a conservative force. A non-conservative force, the best examples would be frictions. Friction does depend upon the path, because as you have a displacement delta x, friction will be doing work against that motion the entire time. And it does become important how far that delta x is to decide how much energy is therefore lost to friction. Air resistance would be another one, where obviously as it's being interacted with flying through the medium, it does depend upon the path taken, how much energy is lost. So good examples of non-conservative forces are generally friction-type forces. Alrighty, next thing to think about is the term is the statement at the top of the board that the work results in a change in energy, and potential energy is energy that can be used to create motion. So in other words, the idea of potential simply means the object has the potential to use this energy to become in motion. Easiest example again of that is gravity. If I put the ball here, gravity can do work on this object as it falls, and will do so increasing the velocity of the ball as it falls, converting the energy from potential, the capacity to move, to actually kinetic energy, energy of motion. So, let us look into this idea of potential energy. Potential energy is the work that can be done on the object, and we abbreviate it U. U for potential, because you have so much potential, right? So, UG would be potential energy due to gravity. Perhaps you write that down. US would be potential energy of a spring. Potential energy due to gravity is the work that can be done by gravity. The potential energy of a spring is the work that can be done by a spring. Now, normally there would be a negative sign. There is a relationship between work and potential energy which states that work is the negative change in potential energy. We state that work is the negative change in potential energy because as work is done upon the object, there is less and less potential as it goes. With the example of our ball, if it was to start at a height here of, let's say, h, and then fall, as it continues to fall, it had a potential energy of, let's say, mg and h at the top, if this is h. And as we go, we start to decrease that energy. If it's at a height of 1/2, Now it only has mgh divided by 2. As the ball continues to fall, the work that gravity is doing on the object is taking away from the potential energy. You can look at the potential energy as the currency of motion. The more potential you have, the more currency of motion you have, the faster the object can become. Which is why if you drop something from a greater height, it always ends up going faster near the ground if we ignore air resistance. Obviously, if we take air resistance into account, there is an outside force acting upon the object, taking away energy from the system. It would be a non-conservative force. Well, if work is equal to the negative change in potential energy, the change in potential is therefore equal to the negative integral of force with respect to displacement, because work is the integral of force with respect to displacement. So our change in potential would therefore be equal to the negative integral of force with respect to displacement, x. So potential energy of the spring and of gravity, if we know it's just the work done, well, the work done on any object due to gravity is mass times gravity times our change in y. And it turns out that our potential energy of gravity is going to be mg delta y as well. The potential energy of a spring, it will be 1/2 kx squared. If you recall from the previous video where we did the integral of the force of a spring to find that the change in energy, the change in energy would be 1/2 kx squared final, or initial, minus 1/2 kx squared final. In this case, it is the negative of that work, so rather than being final or initial minus final, now it would be final minus initial. So, take a little time, look back in your notes to make sure that makes some sense. If not, please ask questions when you come to class. I'll gladly go over that with you. And if necessary, I can also make another video to go through the idea just to make sure it's concrete. So, let us give this idea of energy being converted another step to say that if the energy of a system is constant, if we state that the energy is conserved, that mechanical energy is conserved, when the total work done by all external forces taken from all internal forces must equal 0. In other words, if there is work done on the object and there are internal forces, the sum of these results must be 0. If there's no internal forces, then the sum of all energies must be a constant. It always must have the same value. This is to state that basically the energy before an event occurs must be equal to the energy at the end of this event occurring, minus any impacts due to friction. We get into that in a later lesson. If this is true, and the energy at the start of a situation would be the sum of all potentials and the sum of all kinetics initial, we can state that we basically have any and all potentials at the start plus any and all kinetic energies at the start must be equal to the same logic at the end, which would mean that our potential at the end, any and all potentials at the end plus any and all kinetic energy at the end must equal the same value, which therefore means they must be equal to each other. If this be true, we could basically say, well, do we have any potential energy of a spring at the start? Do we have any potential energy due to gravity at the start? Do we have any kinetic energy at the start? If we have any of these, we would fill in values for them, and then we would state that after the situation occurs, which depends upon what's going on, we can then decide what must have happened to the objects in the process. In other words, if I drop this pen from here and it falls, the potential energy that it had at the top, the greatest point of its descent, must be converted into kinetic energy as it falls. If we assume the height is 0 here, then I can say all of my potential energy becomes kinetic at this point. And it does become important that we declare where is a height of 0, because the energy is conserved in any given situation, any given system. So take the object and consider it moving from here to here. Let's declare that the height is 0 here, meaning that any and all energy it had to have here, it had to have the exact same amount here if we ignore air resistance. We'll have to do so for our first examples. Let me take you through a first example to see if this can make some sense to y'all. So, read the question over and then give it a shot, and I'll solve it shortly. So we have a ball falling from a height. The ball has no known mass. That's unfortunate. That might make things complicated. But we do know that it's falling from some height of 20, and it will end up on the ground. I'm going to decide that the height is 0 at the ground. So its initial position here, its delta y, I guess I could say, or its y initial position, would be 20. Its y final would be 0. It has no velocity at the start. We'll assume it was dropped from rest. And I don't know its velocity at the end. Now we start thinking about, well, if we ignore air resistance, we can assume energy is conserved. So the energy at the start must be equal to the energy at the end. So what types of energy does it have at the start? It clearly has potential energy due to gravity. So there must be some UGI. There is obviously no spring attached to it, so there's no spring energy here. It has no initial velocity, so there's no kinetic energy. This must therefore equal all the energy at the end. It could have potential energy due to gravity. However, I've decided that it is at a position of 0 at the base. It has no potential energy if it has a height of 0. Again, if I plug into this equation, if we use the simplified version, which is to say mg times h is 0 at this point. If I was also to just simply use mgy, my y position is 0 at this point, so I still get 0. So I know it has a velocity, which means it has to have kinetic energy. And there's no spring on the ground, so it's not like it's going to fall into a spring and store energy in the spring. So we won't have potential energy due to a spring. I then write out the equations for these. So mgyi is therefore equal to 1/2 of mvf squared. These are the equations for each of those variables, remembering that mgh is mgy, or I'm sorry, potential energy due to gravity is mg times y. Kinetic energy is equal to 1/2 mv squared. That's where I got those two relationships from. And I placed in their initial for initial position for my potential energy, and vf for it being the final velocity. It's convenient that the masses are identical. I can divide both sides by m. I'm solving for v, so I'll also multiply by 2. I'll end up with 2gy is equal to vf squared. And it's a simple thing to take the square root of both sides. And I'll find that my final velocity is 19.8 meters per second. Please double check that you do get that result. It would be 2 times 9.8 times 20 for the height, for the initial position in this case. Oh, I'm sorry. yi. And my initial position was positive 20. So final velocity was 19.8 meters per second. Let us try another one. Read the question over and then give it a shot, and I'll solve through it shortly. Alrighty, so usually this would be solved with kinematics, and that would seem convenient as the ball obviously goes through this path. We're looking for its maximum height here, and I could easily solve the parabola and figure out exactly where this height occurs. I could also try to solve the maximum point by taking the derivative of my position function for y. That would be another option. But let us try the conservation of energy method. So we know at the start of this situation, and I'm going to decide that my initial height is 0 here, or my initial position yi is equal to 0. And I'll say that my final position here will be some yf, some maximum height that I can get to. But I'm declaring that a height of 0 is at the ground level when it gets kicked, which is important because that means I do not start with potential energy due to gravity. So if I'm to state that energy is conserved, we're ignoring air friction. I start off with, well, no potential energy due to gravity because my height's 0. There's definitely not a spring here, so I don't have potential energy due to a spring. But I do have kinetic energy because it is being kicked. It has been kicked, I should say. It already has a velocity of 12 meters per second. It then goes into the air and flies to the top of its arc. And now it's important to make some distinctions because it clearly still has a velocity. I'll do vt for velocity at the top. And it also has some height that's been risen to. So it clearly has potential energy due to gravity, but also has kinetic energy. So it has kinetic energy, and it has potential energy due to gravity. Well, let us break these equations down. recalling that the equation for kinetic energy is 1/2 mv squared, this is going to become a slight concern. But if we think back to our motion here, it has no vertical velocity at the peak, which means that the component of velocity that it must have, we look back to the start, we had some horizontal velocity, Vx, and some initial vertical velocity, Vyi. The horizontal velocity has not changed because there's no force that can do work on it horizontally. So this must still be Vi cos theta at the peak. The horizontal velocity must still be the same value, and if I solve this triangle, I would get Vx is Vi cosine of theta. So I'll plug that into here where I'll say 1/2 mVf, but I know that Vf is the same as Vi cosine of theta squared because it's 1/2 mv squared, plus m times g times my final vertical position. Keeping in mind that potential energy is energy due to a position. Where is it? Determines what kind of energy it has. Whether it be a spring, where is it compared to equilibrium position? If it's gravity, where is it vertically with how much work can be done due to gravity? Again, conveniently, the masses cancel out. And we are solving for Yf. So it looks to me like I have 1/2 of Vi is equal to 1/2 of Vi cosine theta squared, all of that, Gyf. And I'll take a little time to do my algebra. I'm subtracting my portion here from both sides. Oops, I left out a square. I apologize for that. I'm sure there's some people out there who were nervous about that before. There we are. And all that's left is divide by g. But seeing as we have all the values now, it might be good just to plug into your calculator and find that your answer indeed becomes h of 2.42 meters. So, was it simpler than the projectile methods that we used before with kinematics equations? Well, kinda. It definitely involved a few less steps for some people. It might not have involved less steps for some who are good at taking the derivative and solving for the maximum. There are quicker ways to solve projectile problems, but it is nice to see that this method still holds well and gets us the exact same answer. Please do look back and use your kinematics methods to solve this and find out that the height is indeed 2.42 even when you solve it with the kinematics equations. This final problem looks into the conservation of energy and is a good example of us skipping intermediary steps. So please take a moment, read this problem over, pause the video, give it a shot. Okay, we have a block that's allowed to slide down a ramp of radius 4.0 meters, and it slides down a flat track until it encounters a spring. Spring constant 70 newtons per meter, and we want to find out how far is that spring compressed. Well, it goes from this initial point to this final point where it will compress the spring and will have some maximum compression from rest of delta x. Well, let's see here. Oops. What energy do we have at the start? Because all this is a conservation of energy problem. And there is a point here where it gains a velocity. This is the maximum velocity it has here. We could solve for how fast is it going at the base, but I want to show you that we can skip that step entirely. What energy does it have at the start? Well, it's up a height from the bottom of the ramp, which I will call a height of 0. Or I could also call it a y position of 0, and my height here being my 4 meters. So I start out with gravitational potential energy and nothing else, because it isn't moving yet. I've just let go of it, so it has no initial velocity. Gravity has to do work on it to make it gain this velocity. It then continues down the track and compresses the spring. When the spring is fully compressed, the object will stop. It will be as far in as it can get before the spring will then set it back out again. So at that moment where the spring is maximally compressed, there's no velocity. So its final velocity here is 0, no kinetic energy. It's at a height of 0, no potential energy due to gravity. but it has compressed the spring, taking the spring from a position of 0 to some delta x that we'll have to find, which means that it ends with potential energy of the spring. So, let's plug in what we know. mg times my initial position yi is equal to 1/2 of k x final squared, because its initial stretch would be at 0 and would have no potential. Now that it is stretched to some final position from its rest position, it is at some final position xf and will therefore have potential energy of the spring. Can't cancel out masses in this case because, well, we don't have a common m on both sides. There doesn't seem to be a lot I can change on this one, so I'll just simply do some algebra. I'm going to multiply by 2 over k on both sides. Reason being is I need to cancel out this half here and the k there. And it ends up being 2mgyi divided by k is equal to xf squared. And then simply take the square root of both sides and plug in numbers. At this point, all you have to do is plug in the known values we have. Our mass, our gravity, our initial position, and our value for k, which did not need to be converted because it was in newtons, which is standard for us, and also meters, which is also standard for us, which is convenient. You should find out that your answer is 1.3 meters. I hope everything went well. If you have any questions, please let me know. Thank you for your time, and see you next video.